So we come to the first tool of analyzing nonlinear systems, and this tool is general in the sense that if you have a two-dimensional system, then it is general for any system. So this is basically a graphical approach. So basically you plot the trajectory of the system in the two-dimensional state space, and from that trajectory you can draw some conclusion about the behavior of the system. However, this is not general if you cannot extend it for systems which are more than two-dimensional. Yes, you can say three-dimensional plot also we can actually have, but it becomes difficult to interpret, and beyond three dimensions there is no such plot that you can actually go for. So what are these phase portraits? Now let us understand step by step. So for any autonomous system x dot equals to fx, you can always draw the fx. So you can calculate, if you know the x at a particular point in the state space, you can draw fx at that point with direction and length as per the fx. So it is like that. If you have a state space x1 x2 at any point x, so you know this is the vector x, you know what your x1 and x2 are at this point, and you calculate your f x1 x2. So you calculate your f is what? F is basically f1 x1 x2 and f2 x2 x1 x2. So you will calculate this f1, you will calculate this f2, and this will form a vector f which is having some magnitude and direction at this point. Suppose that magnitude and direction is like this. So you can always draw these small arrows which are the fx arrows at any point in the state space. Suppose these are some arrows which we can draw at in the state space. So you can draw all these arrows. So when you draw all these arrows from many different points in the state space, what you create is basically a field of velocity vectors. Fx is a velocity vector. So you create a field of velocity vectors which is called the vector field. This is called the vector field of the system. So sometimes we draw only the directional arrow and all arrows of equal length. So here I have almost drawn it like that, all arrows of equal length, because what we are interested in is the direction only. We are not interested exactly in the magnitude, we are interested in the direction, in which direction the velocity vectors are pointing. What is the direction of the vector field? If you also draw the length as per the magnitude, then also you have an idea of the strength of the vector field at that particular region, or at a particular point you have the idea of the strength of that vector field. So it is very important to note that this is the vector field only what you are drawing, and it is not the trajectory. This is not the trajectory, this is only the vector field that you are drawing. With the help of these vector fields, now you can actually draw a trajectory. How? You can start from any initial point x0 and move along fx0. So you have a point x0, this is the point x0. Suppose this is the entire state space, this whole screen is a state space. So you have a point x0 and you have a direction fx0 in this direction. So you can move a bit. So you don't have to move along the entire length of the arrow fx0. You can only move a bit in this direction, arrive at a new point x1, and at x1 suppose my arrow is like this fx1. Then you move along fx1 then you move along fx1, arrive at another point x2, you move this much, and from here suppose the arrow is like this, so this is fx2. So in this way you keep on moving and keep on following the velocity vector. Then what will happen, you can join all these points x0, x1, x2 and other points x3, x4, all those points, and you will get a trajectory, you will get a trajectory of the system in the state space. So starting from x0 you will get a trajectory. Now you change the initial position a bit, you will get another trajectory, another trajectory. So a family of such trajectories from a large number of initial states can be drawn. A family of such trajectories from large number of initial states can be drawn, and this constitute the phase portrait of the system. A single trajectory does not form the phase portrait. A family of trajectories form a phase portrait. So now you have a more or less understanding how the system behaves. You will obtain a sort of a behavior of the system by looking at the phase portrait. You will come to understand a behavior. However, this behavior is only a qualitative behavior. This is a qualitative behavior because you cannot actually fix this is the time in this trajectories is implicit, means it is hidden, it is not explicit. So the relationship is not time based, you are only getting a trajectory of the system, you don't know exactly where the system is at a particular time. So it is not exactly quantitative in nature, it is a qualitative behavior, whether the system is converging to a certain point or certain region, or as you have seen in the van der Pol equation, whether it is converging to a limit cycle or whether it is diverging from the limit cycle. All these information, qualitative information, can be obtained from the phase portrait analysis. So let us look into phase portraits. While looking at phase portraits, though we understood that we can in general form a phase portrait for any two-dimensional nonlinear system, however, from the analysis point of view, we will restrict ourselves to the analysis of phase portraits of 2D linear systems right now. Linear systems we will restrict ourselves to, because obviously nonlinearity can be any sort of nonlinearity, so it is not worthwhile to pursue all the nonlinearities. Whenever you have a nonlinear system, you can actually go and see the phase portrait. You can draw the phase portrait in simulation software and then analyze it, then look at it, and you understand the qualitative behavior. However, since 2D linear systems are very specific, we have only a few types, we analyze them and study their behavior. This will also help us in a certain way when we are actually doing some linearization of the system. This we will come at the later part of this particular lecture only. So let us start with linear systems. So when we have a linear system, we will actually analyze not even x dot equals to ax in any coordinate, we will analyze in the modal coordinates. We will analyze in the modal coordinates. This is the this is a system in the modal coordinate where J is basically the Jordan canonical form. Okay, the Jordan form. So you diagonalize the system, or if there are repeated eigenvalues, you make the Jordan form of the system. You come to the Jordan form. Then you have the modal coordinates. What is mean by the modal coordinates? In the modal coordinates, the eigenvectors are the coordinate axis. This we have already seen. This we have already studied. So we come to the modal coordinates using the modal matrix transformation, and here we will analyze the phase portraits. So the behavior that we will see in the modal coordinate is also the behavior in the original coordinate. The qualitative behavior will remain same. So qualitative behavior means whether convergence is there, whether divergence is there, this behavior will remain same. So when we are in the modal coordinate system, the J matrix for two-dimensional linear systems, the J matrix can have only these forms, these four forms. The eigenvalues can be real and distinct, the eigenvalues can be real and repeated, and there are two forms of real and repeated, one with two Jordan blocks, so here there is a 0, and another with only a single Jordan block, so here there is a 1. And complex conjugate. If complex conjugate means eigenvalues are alpha plus minus j beta, and then the J matrix takes this form, the Jordan block takes this form, alpha minus beta, beta alpha. Now we look into the one by one. What is the phase portrait? So first, real and distinct. When we look at real and distinct, we can have a small short analysis. So this is the dynamical system, z1 dot equals to lambda 1 z1, z2 dot equals to lambda 2 z2, and from here we can get the solution z1t and z2t, and from that we can actually have a relationship between z2 and z1. Note that basically this is the trajectory. The trajectory means we are actually finding out a relationship between z1 and z2. That will give you the trajectory. If you then plot for various z1 and z2, you will get the trajectory in the state space. So this is the equation of the trajectory, and C is having this form, and lambda 2 and lambda 1 are of course the eigenvalues. Now if the eigenvalues are positive and distinct, then you will observe that if you draw the phase portrait, also from these equations, if you do some analysis, you will observe that your system will always move away from the origin. The system is having a behavior which is moving away from the origin. You can see these small arrows, these are the vector fields, the small arrows are the vector fields. You can see all the vector fields are pointing away from the equilibrium point. So these trajectories are having arrows on them like this, and this is a typical nature of the trajectories in modal coordinates for these systems with positive and distinct eigenvalues. In the modal coordinate, it will look like this. In the original coordinate, it will also depict a behavior like this, that you will see all the trajectories moving away from the origin. However, the exact shape of the trajectories or the exact phase portrait that you will get may be different. So we basically draw it like this. So we draw the axis when we are drawing freehand. So here it is a portrait from the MATLAB. When we are drawing freehand, we draw the z1 and z2 axis, then we draw the trajectories like this, we draw, and we give the arrows on the trajectory. This is very important, to give the arrows. The arrows will show you the direction of movement, because now you will see that if I change basically the eigenvalues, if I take both negative and distinct, then we have a similar nature of the phase portrait, but the arrows would now be pointing inwards. So in all these trajectories, if you draw freehand, you have to put the arrows also in the trajectories. When you are drawing freehand, you don't need to draw the vector field. This is a MATLAB generated plot, so the vector field is also there. But when you are drawing freehand, you only draw the trajectories and also give the arrows. So here, when we have both negative eigenvalues, then all the trajectories will be pointing towards the origin. which is the equilibrium point. If you have one negative and one positive eigenvalue, then the situation is very interesting. Then what happens, along one eigenvector you are trying to reach the origin, but the other eigenvector will always try to push you away from the origin. So the net resultant vector fields will be along one eigenvector it is trying to come towards origin, and along another eigenvector it is going away from the origin. So one will be like this, another will be like this. So the resultant vector will be something like this. So you see, in all cases the resultant vector is slanted and pushing the system away along one of the eigenvectors which is having a positive eigenvalue. So here lambda 1 is 4, so you can see we are being pushed away along z1, okay. But along z2 if you see, you are trying to move towards origin. So if you are actually starting on x2, you will actually reach origin. If you are starting on x2, you will reach origin, because on x2 the direction is like this entirely. On x2 the direction is like this, you will reach the origin. However, the origin is not stable in nature. We use a different color. You will reach the origin, but the origin is not stable in nature. So if there is a slight perturbation, and the perturbation is not guaranteed to happen along the z2 axis, the perturbation can happen in any direction. If there is a slight perturbation, then the system will move away and it will go anywhere, go to infinity. So this system, this origin is not a stable origin, and this is called this sort of a phenomenon is called the saddle point. This origin, this equilibrium point is called a saddle point. The equilibrium point is called a saddle point. I forgot to mention the equilibrium point of the earlier ones. These are called nodes. When we have definite stable and unstable behavior and these are called the nodes. So nodes, why? Like, because all the trajectories are either originating from this point or converging to this point. So that is why it is called a node. Now here it is a saddle point. It is called a saddle point. Why it is a name so, I don't know so much. So this is called a saddle point. This is a very typical behavior where along one eigenvector you are reaching this equilibrium point, but along the other eigenvector you are going away from the equilibrium point. So this sort of a phase portrait is obtained in that case, and here the equilibrium point is called a saddle point. When you have real and repeated eigenvalues and you have a 2 Jordan block, you see, then it is very simple. You can actually do an analysis very straightforward. The analysis is shown here also. I will not go through it in details. It is very simple. It is only straight lines which is connecting you to the origin. It is straight lines connecting you to the origin. So if you have positive and repeated, then you are having you are diverging away from the origin. The arrow directions you have to give. The arrow directions in each of the trajectories will be diverging away from the origin. And if you have negative and repeated, then again you will have straight lines, but you will have converging to the origin. So each of these trajectories are converging to the origin. Now if you have a single Jordan block, then things become interesting. Note that we have made this 1, before it was 0. So if this means it is a single Jordan block, In the case of a single Jordan block, the analysis is there. Actually this should not be the analysis, it should be z1 dot is lambda z1 plus z2 is there, and the solution z2t is right, but z1t is not this one. It would be something different. So we are let us not spend time here because this is not interesting. The interesting thing is the diagram actually. So let us look into the diagram. You can do the mathematics yourself also and find out exactly what is the relationship. This is not the relationship. You can find out the relationship between Z1, Z2 and Z1 here, how it will happen. So the diagram is more interesting. Here you see, if you have positive and repeated eigen values in case of a single Jordan block, you will have almost, you see the straight lines are almost there, but you are also having some curvature in these lines, so it is curving away. So it is curving away from the origin, and you have to give the direction on the trajectories when you are drawing freehand. Same thing happens for negative and repeated. So here also please correct all these things. So correct these things, and here also you are approaching the origin along a curvature. You are approaching the origin along a curvature in this case. So you have to give the arrows. So the drawing is a bit, you have to curve the arrows a bit, and also notice the direction. So the curving away from the origin is having a definite direction, curving into the origin is having another direction. So you have to note that. So you should not draw this direction and have arrows coming inside. That would be wrong. So the arrows come inside from the opposite curvature. Okay, so you can understand, I hope, by looking at these two figures, that the curvatures are having two different directions of approach in the at the origin. If you have complex conjugate poles, if you have complex conjugate poles, then the analysis stands as I have given here, and we can actually see that if you transform to the polar coordinates r theta, then you have a very simple relationship, this one, which indicates that r is increasing linearly and theta dot is having a constant evolution. That means theta is increasing in a constant rate, and r is increasing proportional to what the r is at present. So it is basically the equation of a spiral. So if you can also write the solutions like this, and it is a spiral in the z1 z2 plane, and the direction of the spiral will depend on what is your what is the real part. If the real part is positive, then you are basically diverging away from the origin. You are basically diverging away from the origin, and you have to give the arrows in the trajectories, and this is a unstable focus. So here it is not a node anymore, it is not called a node anymore, it is called a focus. So it is almost like a hurricane or a something like that, a wind pattern sort of thing you can see. So that is why I think it is called a focus. And if you have negative real part, then you observe that the curvatures have changed their direction, and of course now you will have arrows pointing inwards. So you have a stable focus in this case. You have a stable focus if your real part is negative. What happens when you have your zero real part? If you have a zero real part, then what happens, what change happens, your r dot becomes 0 basically, and your rt is r0. So the radius does not change, but theta dot is beta, so theta changes. That means you are getting circles, you are getting concentric circles. So if your alpha is 0, you are getting concentric circles. This is called a center. This sort of phase portrait is having its equilibrium point at the origin, but it is a center equilibrium point. So if you start there, then you will be there, otherwise you will be in concentric circles around that. So now just a roundup of what we studied about the phase portraits of two-dimensional linear systems. We have these several types of phase portraits that we saw, which happened for different situations. but mainly these are the types. What are the types? Stable node, unstable, this should be unstable node, sorry, this should be node. Stable node when we have negative real eigenvalues, unstable node when we have positive real eigenvalues, both distinct in nature. Saddle point, one negative, one positive. Stable focus or spiral when we have complex eigenvalues with negative real part. Unstable focus or spiral when we have complex eigenvalues with positive real part. And center when we have complex eigenvalues with zero real part. So the diagrams you can see here now, this is the way you should draw basically. This is the way you should draw in freehand and with the arrows and all. So these are the different types of equilibrium points of two-dimensional linear systems when you are doing phase-ported analysis. Why this is important? So this is we have come to understand the linear systems now, but with the understanding of the linear systems we can have some understanding of the nonlinear system also. So this is why where analyzing the linear two-dimensional linear systems became important, because always you don't need to actually analyze the nonlinear system. You will get very different phenomena in the nonlinear system even when you do phase-ported analysis. So normally what happens, we will linearize the system, and once we linearize the system we can now readily understand what type of equilibrium point I will have, and that understanding you can extrapolate to the nonlinear systems in certain cases. So that is what we need to keep in mind. So and that is what we are studying in this now. So when we have to linearize the system, so that is the fundamental thing. So if we are to use the understanding of the linear systems phase portrait analysis, or as a matter of fact any linear systems analysis method, if we want to use to analyze the nonlinear system, we have to first linearize the system. So linearizing the system is basically evaluating the Jacobian matrix at the point of at the reference point, or at the point of interest. What am I trying to say? So you see that what is the Jacobian matrix. So what is the Jacobian matrix? Jacobian matrix is the matrix of the partial derivatives. So your x dot equals to fx, this is basically f1 x1 to xn up to fn x1 xn, correct? So you take, so the Jacobian is formed, the first row you take the first function, have the partial derivatives with respect to all the variables x1 to xn, write them down, dou f1 dou x1 dou f2 dou x2 dot 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 dou f1 dou xn. Then the next row, dou f2 dou x1 dou f2 dou x2 dot 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 dou f2 dou xn. In this way you come to the last row, which is dou fn dou x1 dou fn dou x2 dot 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 dou fn dou xn. This is the Jacobian matrix. So you can always do the partial derivative of the function with respect to all the variables, and you can figure out so the Jacobian. Remember, this is partial derivative. So when you are taking the derivative with respect to x1, you are assuming x2 to xn are constant. So this is what you should keep in mind. This is the Jacobian, is the matrix of the partial derivatives. Now if the system is to be linearized about a reference point xr, if the system is to be linearized about a reference point xr, then you have to basically evaluate the Jacobian jr at x equals to xr. So this is the Jacobian j. This Jacobian is general Jacobian. This is not evaluated at any particular point xr. So after calculating this Jacobian, now you put the value of x as xr, then you are evaluating the Jacobian JR. So with that Jacobian JR evaluated, the system becomes linearized about the reference point x equals to xr, and the linear system is x dot equals to jrx. This is the linear system, the locally linearized system. The system behavior near the reference point can be expressed by this linearized system to a certain degree of accuracy. As we move further away from the reference point, what will happen? Of course, the system behavior will deviate from this linearized model more and more. So if we can go for piecewise linearization, and we have to have another linearized model for another reference point if needed. However, that is complicated actually. What happens basically in many systems, in general many systems are even big industrial systems, any sort of systems, control system, the main basic purpose is basically to generate a desired output. So the output level, or there is a desired reference level in which the system needs to operate. The operational point is given for the system. We need the system to operate at this particular operational point, at this particular reference point. So that is known to us. What is that reference point? So what we do normally, we linearize the system about that reference point. Somehow we take the system to that reference point, and then we analyze the system about that reference point, and then we design a controller or whatever in order that the system remains at that reference point. Whatever small amount of deviations it suffers, we design a controller so that it quickly comes back to the same reference point. So this is how linearization is done. Now there is a very important theoretical discussion on perturbed systems. What are perturbed systems? So if you have a linearized autonomous system, this x dot equals to ax, you can suppose this as a linearized system now, and you can suppose that delta A is a perturbation matrix consisting of uncertainties and non-linearities. So basically x dot equals to A plus delta AX now becomes a uncertain or a non-linear system, delta A consisting of the uncertainties and non-linearities in a very local region. We have to think in this manner. This delta is also in a very local region. Now the theory says this, that if the magnitude, and this theory is very intuitive in nature, you can also agree to this theory readily. If the magnitude of perturbation in each of the element A is delta A, it will be is less than this some value delta which is positive, then the eigenvalues of the perturbed matrix A plus delta A will lie in open balls of radius epsilon greater than 0 centered at the eigenvalues of A. So this is too much a lengthy sentence. What it is basically saying is that you have some eigenvalue. So this is the plot sigma j omega, the complex frequency plot. You have some eigenvalue somewhere. Suppose a real eigenvalue here. You have an eigenvalue of the matrix A. So this is an eigenvalue of the matrix A. Now you have some perturbation, it is there in delta A. So delta A, with the perturbation, it is creating a matrix A plus delta A. So the question is, what about the eigenvalues of this matrix? So it is saying that if the perturbations on delta A is less than this quantity, basically this is a very small quantity, you should assume. If there is a very small disturbance then the eigenvalues of this matrix will also be slightly disturbed. That is what it is trying to say. So this open ball of radius epsilon greater than 0 centered at the eigenvalues of A is means this ball, basically there is a ball now, there is an open ball now of radius epsilon centered around the eigenvalue. So the new eigenvalue of A plus delta A will be in this region, exactly where no one is telling you, but they are saying that it will be in this region. Exact eigenvalue they are not giving you, only they are saying that your new eigenvalue will be in this ball, in this region around the original eigenvalue. So if the perturbation is very small, this epsilon is also very small. So this is what you need to consider, that the perturbation is very small basically, and hence the eigenvalue is perturbed, the eigenvalue is also suffering a perturbation and it is perturbed very slightly. So if that is the case, then you start reading these bullet points. Now if the eigenvalue is in open LHP, open left half plane, open left half plane means the left half plane without the imaginary axis, the open left half plane or the open right half plane will remain in its respective half upon arbitrarily small perturbations. If the perturbation is arbitrarily small, then the deviation in the eigenvalue will also be arbitrarily small. Arbitrarily small deviation, if the eigenvalue is in the open left half plane, it will never be able to cross the left half plane. That is what it is saying. It will remain in it will remain in this respective half. So it will not even, it is very close. Suppose you have a very eigenvalue very close to the imaginary axis, but however close it may be, since you are considering arbitrarily small perturbations, your perturbation in the eigenvalue will also be arbitrarily small, so that it will not reach the imaginary axis also. So this is the beauty of limit mathematics actually. So the concept of limit is there. So in the limiting case also you will not be able to reach the eigenvalue in very small perturbations if you have. If the eigenvalues are on the imaginary axis, then a small perturbation will change the eigenvalue, will shift the eigenvalue to either the LHP or the RHP. This is also fine, I guess, because the value will change from the imaginary axis, it is going either left or right. So it can go either way, it can go anywhere in the ball. Basically the ball constitutes of any direction, so it can go to the left half plane or the right half plane. So there is a possibility of the eigenvalue losing its nature of being on the imaginary axis. If this happens, then what is the consequence? Basically consequence is this, that the node, focus and saddle point, which are having very definite eigenvalues, either positive or negative, so the node, focus and saddle point will remain same for sufficiently small perturbation. Node either positive eigenvalues or negative eigenvalues, so they are not on the imaginary axis. Focus not on the imaginary axis, focus is with complex eigenvalues with either positive real part or negative real part. Saddle point, one positive one negative, they are never on the imaginary axis, so they will remain the same, the equilibrium point will remain the same type even with sufficiently small perturbations. However, the center equilibrium point is where we have complex eigenvalues with zero real part. That means the eigenvalues are on the imaginary axis, so they will change. So if you have a center equilibrium, if you had a central equilibrium point for x dot equals to ax, if you had a center equilibrium point for x dot equals to ax, the actual system, which is a plus delta a, the perturbed system, will actually not be having the same type of equilibrium point. So in this case, you will not be able to conclude about the nature of the equilibrium point by studying the equilibrium point of the linearized system. However, if the linearized system exhibits equilibrium points which are node, focus and saddle point, then the perturbed system will also have same type of equilibrium points. This so this is the phenomenon which is happening, and for this we categorize the equilibrium points as structurally stable and structurally unstable. So there is a new category given. So the node, focus and saddle point are called structurally stable equilibrium points because suffering small perturbation, they are not changing the nature. However, the center is structurally unstable because any small perturbation will change its nature absolutely. Either it will become a focus, stable focus or an unstable focus. It may also become something else. And node also it can become depending on exact location of the whether they are very close to zero, exact location of the eigenvalues. So it is structurally unstable. Now it will not remain a center anymore. That is all we need to understand. So the conclusion is that eigenvalues on the imaginary axis are vulnerable to perturbations, and we have a different category of terminology which is called hyperbolic equilibrium points. This we refer to those equilibrium points where we don't have a zero real part. So none of the eigenvalues will have a zero real part. So even if you have real eigenvalues with 1 as 0, then it will not be hyperbolic. So none of the eigenvalues should be 0, should have 0 real part. So now some more statements can be made, which are these, that for the 2D system with a single eigenvalue at the 0, so if you have a single eigenvalue at the 0, that means it is a set of real eigenvalues. One eigenvalue is at 0, another eigenvalue either in the left half plane or in the right half plane. Now the perturbation will lead to so it was basically a saddle point. Sorry, it was not a saddle point. Sorry. So it is a phenomenon where you have an eigenvalue at 0. So it is a non-hyperbolic case basically. So eigenvalue is 0. Another eigenvalue is somewhere either in the left half plane. So this is the 0. Another eigenvalue is in the left half plane or in the right half plane. We don't know, but when we have a perturbation, this particular eigenvalue is shifting. Either it is shifting to left half plane or it is shifting to right half plane. So if it shifts to the same side as the other eigenvalue, then it will be a node. And if it shifts, if it is in the right half plane, if both are in the right half plane, it will be unstable node. If both are in the left half plane, it will be stable node. Another case can be that the eigenvalue shifts to the side opposite to the other eigenvalue. In that case, it will be a saddle point. In that case, it will become a saddle point. Okay, depending on the position of the other eigenvalue, these sort of phenomena can be exhibited. Now, when both the eigenvalues are 0, so if there is a system where both the eigenvalues are 0, then the perturbation can lead to all types of equilibrium point, because it can go anywhere, right? So it was in the 0, both can come to the same side, one can come to one side, another can go to another side. They can also move along the imaginary axis. They can come to any location which is having real and imaginary part. So all types of different equilibrium points can be led to. So it can be a center, it can be focus, node, saddle point, everything there is possibility now. Okay, so in this case all possibilities are open. Now I have actually not shown you the phase portraits when we have a zero eigenvalue, a zero eigenvalue real, another eigenvalue something different, and when we have both zero eigenvalues. So I suggest that you may try to draw some phase portrait, or you can simulate also the phase portraits and see how they look actually. Okay, so with that we come to the end of the lecture, and I hope you understood what is the importance of the phase portrait. So we can analyze two-dimensional systems very easily, and then we saw the the phase portraits for linear systems in the modal coordinates. That is enough, that is sufficient to understand the nature of the equilibrium points. We studied so many different types of equilibrium points. Then we studied whether they are structurally stable or structurally unstable equilibrium points. We understood the notion of linearization and perturbed systems. So the idea of linearization and perturbed system does not only hold for two-dimensional system. This is important to understand. If we have a n-dimensional system like this, and we know that the eigenvalues are structurally stable, then the perturbed system x dot equals to a plus delta a x will also exhibit similar nature of eigenvalues because they are structurally stable. What are structurally stable eigenvalues? So here in the case of phase portrait we have noted down node, focus, saddle point, but basically what we are trying to say is that they have to be very clearly either in the left half plane or in the right half plane. Imaginary axis eigenvalues are not permissible. So if we don't have imaginary axis eigenvalues, then the stability phenomenon of the linearized system, the same stability phenomenon appears in the perturbed system also, even when we have a system of general nth order. This is very important to understand. This is very important to understand. If the order is 2, then we actually can draw up the phase portraits. If the order is not 2, then we cannot draw the phase portrait, but we can analyze the eigenvalues of the linearized system, and if there are no eigenvalues with zero real part, then we are fine to ascribe the stability behavior of the linearized system to the perturbed nonlinear system. So here I would like to end the lecture. Thank you for your attention.